Hi, in this video we will learn when a plane or a line is a subspace in R3. Well, let us start with one example. The example is S1, which is set of all vectors in R3 whose components satisfy this equation x plus 3y minus z is equal to 1. Is this a subspace of R3 or not? Well, first, let me just write this as a note. Note that S1 is the plane x plus 3y minus z equals to 1. Well, sometimes we take it as the points, or sometimes we take the position vectors of those points. And here, now we see that basically we are trying to check if this plane, which is a plane in R3, is a subspace or not. Okay, but well, the checking doesn't change. We have to check all these three conditions. First, is zero vector on the plane, or in other words, in S1. Yes. What does this mean? This means that if I plug in x equal to 0, y equal to 0, and z equal to 0, then does the equation hold? So we have 0 plus 3 times 0 minus 0 is equal to 1. Well, obviously, you see, this is not equal to 1. So that means right away that 0 vector is not in S1. And done. This means that the line, the plane S1 is not a subspace of R3. Well, you can say, okay, this is not, we should not stop here. Well, okay, we want to see in general a plane, or the vectors of a plane. So we can write general form equation. It contains 0 vector if and only if, well, you know, 0 a times 0 plus b times 0 plus c times 0 needs to be equal to d. That, well, sorry, this needs to be 0. So that means that d needs to be equal to 0. And that is exactly what we need to have. The constant term of the general form equation needs to be equal to 0 to contain the 0 vector. Okay, so well, then let's just change the example we had. Now we ask, okay, is S2, which is the set of all vectors of this plane, x plus 3y minus z, and we know that we have to put 0, otherwise 0 vector is not there, is a subspace. Well, we already checked. Yes, 0 is in S2. So that is done. How about the S2 being closed under the addition? Well, for that, we need to pick two vectors. Let U and V be two vectors in S2. Means what? Means that if u has the components x1, y1, z1, and v has the component x2, y2, z2, these are in S2. That means that while we have x1 plus 3y1 minus z1 is equal to 0, and x2 plus 3y2 minus z2 is also equal to 0. Now we can add these two equations and we get x1 plus x2 plus 3 times y1 plus y2 minus z1 plus z2 is equal to 0. And look, this is the first component of this vector. This is the second component. And this is the third component. And what we see here, it means that this guy is in S2. But that is exactly what we were looking for. This is u, the vector u plus vector v is in S2. That means that yes, S2, the equation for the plane or the plane is closed under the vector addition. And we kind of know that. So if you have geometrically, so if you have two vectors on a plane, the vector addition is going to be in the same plane. Yes, no matter which rule of addition you consider here, this is going to be on that plane. So this is 0, the origin. This is u, this is v. And similar computation, well, let u be in S2. That means that if we take the components of this as x, y, z, so this is x, y, z, we now know that x plus 3y minus z is equal to 0. Multiply both sides by any scalar you have. Cx plus 3y minus z equals 3 times 0. And that means that Cx plus 3 times cy minus cz is equal to 0. And well, that means what? That means that c times maybe I write it this way first. Cx, the vector Cx, Cy, Cz, which is same thing as Cu, is in S2. And that shows that the vector is, the S2 is closed under the scalar multiplication. Very nice. And well, in general, this is true for planes. A plane which passes through the origin is a subspace. And actually what we showed above is the only one that contains 0 is this one. So this is if and only if, basically. Well, how you see this in general, the proof I showed above is going to work in general, but there is another way of showing this. Every plane can be written as this form, x, y, z, or vector x's, such that nx equals to np, but this passes through origin that can be 0. And you can see that dot 0 vector is going to be 0, so that satisfies the first thing. The second one is that if n dot x1 is equal to 0 and n dot x2 is equal to 0, then you can conclude that n dot x1 plus x2, which is n dot x1 plus n dot x2, this guy is also 0 plus 0, which is 0. So that means that it is closed under the addition. And the third thing is that n dot x is 0. It implies that c dot n dot x is equal to 0. And that means that n dot cx is equal to 0. That means that cx is on the plane. And well, that is what we have. So what we showed is that, well, if you have an equation like this, that is a subspace of R3. Well, similarly, you can show that lines in R2 are lines, similarly, you can show that lines in R2 are subspaces if and only if they pass through the origin. Okay. So if and only if they pass. So as soon as they pass through the origin, they will become a subspace. There are other lines definitely, but not all of them are subspace. Only the ones which pass through the origin. And I will leave this one as a exercise for you, that you need to show lines in R3 are subspaces if and only if they pass through the origin. It's interesting to know that basically these guys are the only subspaces we have. In other words, every subspace of R3 is either a line or a plane. There's one more case when it is just only the origin, just one point, the origin. That's an interesting fact that you can see in general. Okay, so only the planes and lines which pass through the origin form subspaces for R3.